Next, we'd like to consider how we can graph polar equations. So given a polar equation, r equals some function of theta, we can imagine that our polar curve that corresponds to this equation will consist of all the points who have at least one polar representation r theta that satisfy this equation. As we know, there could be many representations of a single point in polar coordinates. So as looking for at least one point that satisfies one representation of a point that satisfies that equation. So let's just warm up with some very simple curves. What is the curve that goes with the polar equation r equals 2? So if we're imagining what kind of curve this would be, we can consider what points would satisfy this equation. So basically, a constant for the radius means that we're looking at all the points that are a distance of 2 away from the pole. Okay, so graphically we can imagine any point that is a distance of 2 away from the pole would be a point on this curve. So of course any point that's 2 away from the pole would form a circle of radius 2. Is there another way that we could verify this? Well, sure. If we want to remember something about polar coordinates, we can think about how I can also represent this equation in Cartesian coordinates. So given r equals 2, well, let's remember, how would I convert this to Cartesian coordinates? We know that r squared is equal to x squared plus y squared. And in this case, I can replace r squared with x squared plus y squared. So first, maybe we can square both sides of this equation. So I get r squared equals 4. And then r squared in Cartesian coordinates is x squared plus y squared. And there we can see here, this is the Cartesian equation that gives us the circle of radius 2. Okay. So we see in this case, whenever I have r equal to a constant, it's a circle. What would the polar curve theta equals 1 look like? So similar to before, we can think about what kind of points would satisfy this equation. Now in this case, it's setting the angle theta equal to a constant 1. So any point that makes an angle of 1, in this case, remember here, theta is measured in radians, so 1 radian. So any point that makes an angle of 1 radian with the positive x-axis would be a point that's on this curve. So if we imagine now making an angle of 1, where would that land? Probably somewhere in quadrant 1. Remember, pi radians would be 180 degrees. So this is going to be, one radian would be somewhere in quadrant 1. So any point that lands on this line here would be a point on this curve. So we can imagine that any point that lies on this line would be a point on that curve. So positive radius would be on the side that's in quadrant 1, and we can also extend it into quadrant 4 for the negative radius. Okay, so we see here this is a line that makes an angle of 1 radian with the x-axis. How would I represent this in polar coordinates? Or, excuse me, in Cartesian coordinates? Well, let's think. If I were to take theta equals 1, we know that we can convert the angle theta into Cartesian coordinates by using the relationship that tan of theta is equal to y over x. If I apply tangent to both sides of this equation, then over here this becomes y over x. And so we can see here that we get the equation y equals tan of 1 times x. And so tan of 1 here is actually the slope. Let's look at another example. Suppose I want to sketch the curve with polar equation r equals 2 cosine theta. And then again, we're going to look for our Cartesian equation for this particular curve. So first, let's imagine how we can sketch this curve. Notice that we could think of this like the theta is the independent variable and r is the dependent variable. So one way to construct the curve here is to plug in different values of theta and collect the values of r that correspond to that value of theta. So suppose we're just going to sweep through the first quadrant. Let me just evaluate this at several simple angles, ones that we can evaluate easily in the cosine function. Okay, so those would be the angles that sweep through the first quadrant. We know cosine of 0 is 1, so when I do r equals 2 cosine of 0, I would get 2 times 1 is 2. Cosine of pi over 6 is radical 3 over 2. So 2 times the square root of 3 over 2 would just be square root of 3. For pi over 4, cosine of pi over 4 is radical 2 over 2. So 2 times radical 2 over 2 is radical 2. Pi over 3, cosine of pi over 3 is 1/2. So that would be a value of 1 when we multiply by 2. And then cosine of pi over 2 is 0. So that would be 0 there. So let's imagine how these points land in that first quadrant. So the first point is at 0, an angle of 0 with a radius of 2. Okay. Notice here we're going to sweep through the angles down the first quadrant. We have the angle pi over 6. We have the angle pi over 4. We have the angle pi over 3. And then the angle pi over 2. So it's going to sweep through these basic angles here. The angle pi over 6 gives us an r value of radical 3, which we can imagine maybe is something around 1.6 or so. So I can probably estimate it, maybe. Square root of 2 is about 1.4, so maybe a little bit shorter there. And then pi over 3, it's a distance 1 down that line. And then pi over 2 is at 0. So as it revolves around those points in the first quadrant, it's going to form what appears to be a semicircle, right, as it sweeps through those points. Well, let's continue. Suppose I were to go through the second quadrant. Okay, so I'm going to quickly plot those points now as well. So the points here in the second quadrant would be 2 pi over 3, 3 pi over 4, 4 pi over 3, 5 pi over 6, and pi. Okay. Evaluating these points, notice now I'm going to get negative values. For instance, cosine of 2 pi over 3 will be negative 1/2, so that will be negative 1 there. Cosine of 3 pi over 4 is negative radical 2 over 2, so that will be negative radical 2. Cosine of 5 pi over 6 is negative radical 3 over 2, so that's negative radical 3. Cosine of pi is negative 1, so we get negative 2 for that value. Now, since all these r values are negative, notice that as we sweep through these angles here in quadrant 2, we're actually going to plot the points on the opposite side of those angles here in quadrant 4. Because those r values are negative, all those points are going to land here in quadrant 4. Okay? And by the symmetry of it, we can imagine that they're going to correspond pretty well with the angles, or with the points that we found on the top half of this curve. So we can imagine it sweeps through these values and forms the bottom half of this curve. And there it's completed one full rotation. Notice that if I were to plot the remaining curves, it's going to retrace these points again if I were to continue to plot more points. So it looks to me like here we have a circle of radius 1 centered at the point 1, 0. And notice the complete graph was traced out as we went from the angle 0 to the angle pi. What would the Cartesian equation of this curve look like? So for part B here, let's do just a little bit of algebra to get this equation into its Cartesian form. So remember that we know, we know that r squared equals x squared plus y squared, and we know that x is equal to r sine theta, r cosine theta, and y is equal to r sine theta. So how can we use these equations now to convert this equation into its Cartesian form? Well, one thing I could do is, if I want to get r cosine theta in the equation, I can multiply r to both sides of this equation. So that gives me r squared on the left side and 2 times r cosine theta on the right side. We know that r squared becomes x squared plus y squared. R cosine theta becomes x. So there's the Cartesian equation of our circle. But let's do a little bit of completing the square here to show that it is in fact a circle of radius 1 centered at the point 1, 0 like it appears. So I'll just quickly complete the square. First I'll subtract the 2x over here. I'll add 1 to both sides so that this now factors into a perfect square. X minus 1 squared plus y squared equals 1. So here you see it agrees with what we observed here. It's the equation of a circle centered at the point 1, 0 with a radius of 1.